This. All right, I think we are live. Those on the Zoom bridge, holler at me if my volume drops to below a perceptible level, and we will rectify that situation. Welcome to CS 152. Welcome to spring 2004, for that matter. I hope everybody had a really nice holiday. So this is CS 152 and simultaneously CS 252A. Just by a show of hands, who's in 252A? Okay. All right, good. So we have some representation. I think we have like 20, 25 people in 252A, pre-waitlist calling, and the rest of everyone's. So this is computer architecture and engineering and graduate computer architecture. My name is Christopher Fletcher. I'm super excited about teaching this course this semester. I took CS61C as an undergrad here in fall of 2007. Before I took CS61C, I knew I wanted to be a software engineer. After I took CS61C, I knew I wanted to become a hardware engineer. And after taking CS152 in, I believe it was spring of 2009, I knew that I wanted to become a computer architect. And the rest, subsequent 14 years, that is history. I took this class in spring 2009 and as it was in its original form, CS 152, and then I later took CS 250, which is I think like the closest thing to 252A nowadays. So this is my first time teaching this course, period, but also teaching the course in this kind of hybrid form, 152 to 252A. So I'll be kind of discovering how this goes along with you, and suffice to say, if anybody has improvements at any point throughout the semester, there will be ways of submitting feedback so that we can course correct. I'm completely open to changes and ideas. Whoops, this is going to work. Keyboard is not working. I will have to click through. That's okay. All right. So this course is about computer architecture. So just as kind of like some scene setting, today is going to be giving a broad kind of overview of the macro trends in the field. We're going to start by defining what we mean by computer architecture, and then kind of go over at a high level like the quantitative history. Then we're going to go over course administrativia. We'll see how quickly I can do that. And then we'll take a step back and go a little bit more slowly through some of kind of the milestone computer architectures that have appeared in the last 100, frankly 200 years, but mostly in the last 100 years. So let's start with a definition. What is computer architecture? So we have this picture here, application to physics. And as we know, when we work with computers, we don't typically care about what the underlying physical substrate that is performing whichever physical computations that make up our application is actually doing. In the broadest sense, this is the job of a computer architect, to develop a set of abstraction layers to hide the details from an application of the underlying physical machine, what is governed by the manufacturing technologies of the day. This is very important because usually the way that we implement computation is in kind of like a much more low level and primitive form than what we want to work with when we're designing an application. And also, manufacturing technologies are constantly changing. So the goal here is to bridge the divide between hardware and software and give software programmers, application writers, a steady view, and one that hides as much complexity about the underlying system that they're computing in as possible. This usually cannot be done in one step. It used to be able to be done in one step where we had a clean notion of the hardware-software divide. Now it is and has been broken into several steps as a way of, at each level of the hardware software interface culling out additional complexity so that we can build more and more sophisticated systems. We'll be exploring how this has been split up into multiple steps throughout much of the rest of the course. Just to note that this is not how all applications work. So some applications do require this type of abstraction because we do not want to know how the application is implemented under the hood. There are some applications where the application itself and the underlying physical process is fused into one. A great example of this is like a magnetic compass. Like the physics that govern the compass are precisely baked into the compass's design, and it's a fixed function operation telling us where true north is. Okay, so to put this class into context with the rest of the Berkeley curriculum, so here we have the like a bird's eye view of the system stack, starting at the top level applications, going on down to physics. So we say that applications are described as a composition of algorithms. Algorithms are encoded or represented in programming languages. Programming languages compile programs or enable programs to be represented and later compiled into representations that can be run on systems managed by operating systems and virtual machines. Virtual machines interact with the hardware-software interface along with the output of compilers. The hardware-software interface these days being called the instruction set architecture, which gives us a way of expressing what we want to do on the hardware as a sequence of operations or as different operations. The instruction set architecture is implemented by the microarchitecture. The microarchitecture is implemented by gates, register transfer level, RTL, if you've taken CS151, which are implemented in circuits, which are implemented in devices, which interact directly with the physics. And out of curiosity, I assume everybody has taken CS61A through C because that's like kind of the standard lower division prereqs. Who's taken EE 143 or kind of upper division circuits classes that are below the level of 151? Wow, okay. All right. I see 2 hands, 3 hands, 1 hand which is going up more slowly, 4 hands. Okay. Who has taken at least one upper division class above the level of 152, like 170, 164, 162? Okay. All right. How many people have taken 164 or 162? Okay, we have a lot of systems designers here. Interesting. Who here has taken EECS 151? Oh, wow, lots of people. Okay, lovely. We're going to get along. I TA'd that class 4 times in my undergraduate, and it is, I hope to be able to teach it again soon. A lovely class. So this is the application to physics and device stack. The UCB curriculum is designed to kind of give you horizontal deep dives into different levels of the stack. So 170, 164, 162, and then coming up from the other direction, 151 and 251 and 143. And the way or where CS 152 and 252A fits in is more kind of, it's debatable whether it's the instruction set architecture or whether computer architecture should be thought of as being at the level of the instruction set architecture, or these 2 levels, the instruction set architecture and the microarchitecture. So for the purposes of this class, regardless of what we believe computer architecture should be, we're going to be covering ISA and microarchitecture. And recall from what I said a few minutes ago, the ISA is the hardware-software interface. What about the hardware's functionality is exposed to software systems, and the microarchitecture is how the instruction set interface, which is just like an API, if you're familiar with software systems, is implemented. How you actually organize blocks in RTL to implement the different operations in the ISA. The ISA being sets of instructions, different blocks of RTL being responsible for executing or implementing these different instructions. So this is what we're going to be covering over the course of the next semester. And going back to our programmable compass example, despite the fact that fixed function compasses are a thing and that you can build them directly out of magnets for detecting true north, the way that we typically interact with compasses today. This may or may not be true because we're in Berkeley. We're surrounded by nature, and if you're an avid hikist, you probably do, or a hiker, you probably do have an OG compass, but how most of us probably interact with them today is built on top of programmable computers, in which case even the compass has to go through all these different levels to be implemented. So this is kind of where CS152, 252A fits in the Berkeley curriculum. Another kind of way of thinking about what you're going to get out of this class is shown by this diagram here, which we'll come back to in a few slides. You can think of what you learned, in particular, the processor pipeline that you implemented in CS61C as this little like black square here. Do they implement in CS61C a pipelined processor or a single cycle processor? I take it a pipeline processor. Feel free to shout it out. Yeah. Pipelined? Okay. In that case, the black box might be slightly larger. Suffice to say, there is more to it than what was covered in CS61C, and what we're going to be going over in 152 is something more akin to what state-of-the-art commercial processors look like. So this processor here on the right side is the Apple M3. It's the latest in-house Apple silicon that came out just this last year. And just to kind of whet your appetites, the processor pipeline that you implemented in CS61C is analogous to a general purpose core in the Apple M3. A general purpose core in the Apple M3 is either the red cores that you see kind of on the left-hand side or the green smaller cores that you see towards the middle. Suffice to say that these cores are a lot more complex than, if you just consider them individually and zoom in the picture, they will be a lot more complex than the little black rectangle or square that you implemented in CS61C. And clearly there's a lot more going on this chip than just these rectangles labeled core. Most of, I should say, the blue cores up top are not the same as what you did in CS61C. There's just the red, just the green. There's a lot more going on here. And the goal of this course is to kind of bring you up to speed so that you can actually participate in industrial processor design and manufacturing. Okay, so suffice to say, a lot has changed. Interestingly, almost all of this change has happened in the last 100 years. This field moves remarkably quickly, arguably the fastest growing field in terms of innovation is device technology, like transistor shrinking, things like this. And computer architecture, by definition, has to be fast on the heels of that device scaling. Otherwise, it's basically not put to use. So a lot has been done in the last 100 years in this field. It's constantly changing. It's super excited to be working in. This diagram here is the EDSAC. This is a computer that is about 75 years old, so it's not even 100 years old. And it's debatable what is the first stored program computer, but a reasonable approximation is to call it the first actually constructed stored program computer, where program and data are one in the same. And this is kind of the world that we live in today. Now, that was where we were 75 years ago. A lot has changed at a rapid clip. A lot of the core ideas are still present. So what you didn't see from the EDSAC is that it got right many of the concepts that we still use today. For example, a set of operations made up of arithmetic, data-dependent control flow, and memory access. These are the kind of three spokes of the wheel of modern instruction set architectures. So some of the core concepts, many of the core concepts are still around today, but of course a lot has changed from device technology, which has influenced microarchitecture, which has influenced application and so forth, and also device form factors. So we have everything from wearables to portables to data centers to new and exotic types of I/O that enable new immersive experiences like XR. So clearly a lot has changed from the EDSAC in the late 40s. And another kind of like take on why this field is kind of so dynamic and exciting to work on is that it kind of sits between applications and technology, and it's influenced by both sides of this coin. So application drivers influence computer architecture and tell us how and where to innovate. Device technology, as it changes, tells us where we need to innovate. Because again, without computer architecture creating that level of interaction between hardware and software, the innovations in device technology ultimately cannot be used. So I want to kind of like hit on an example of like both sides of this coin. So on the application side of the coin, everybody here knows who Jeff Hinton is? Yes? Everyone knows what deep learning is? I see more heads nodding. Okay. So Jeff Hinton is kind of colloquially called the godfather of deep learning. And it was 2013 when I was a graduate student. I'd been working on hardware security and I wasn't really paying attention to the deep learning revolution. The AlexNet breakthrough had happened the year before. And I was TAing a performance engineering course and we had Jeff as a guest lecturer in this course one day. And I came and sat down, and from my perspective, there was just another guest lecturer in the room, but the room was packed. I was like, what is going on here? Who is this person? And he starts talking about the last 40 years in deep learning. And it wasn't even in that lecture that I really started paying attention, but soon after I started paying attention. But he did have this, he had this great quote in the lecture that I still remember today. And that quote is that over the past 40 years of working on, it wasn't called deep learning until recently, neural networks, I being Jeff, had come up with algorithmic improvements to deep neural networks to make them go 1 million times faster. This was primarily backpropagation in the early 80s. And computers had gotten 1 million times faster. So he made the point that, yeah, I've done a lot of good work in this space, but it was only through the combination of innovations at the application and the algorithm level, the software level, and also simultaneously the hardware, that we were able to get a big enough improvement for deep learning to really take off. So from the application side to the computer architecture side, not only more recently, of course, has computer architecture been has been significantly influenced by deep learning, but applications, deep learning has also been heavily influenced by computer architecture. So that's kind of on the applications to the architecture side. And I just realized this little red button or this little red knob indicating recording, I thought it was pause recording. Okay, good, it's still on. I had this fear that I had hit the wrong button. We're all good, okay. So from the applications to the computer architecture side, there's been a lot of innovation and kind of feedback on both sides. Between the technology and computer architecture, there's been a similar kind of synergy with architecture influencing technology and vice versa. Perhaps the most, or kind of like the first that you'd learn example of this is transistor scaling, which we'll see a little bit more in the next few slides. So we have transistors shrinking, which means that your clock frequency has a potential to increase because as transistors shrink, the effect of the speed of light between adjacent transistors, which you can think of as adjacent logic gates, if you've taken CS 151 before, is shrinking. As the clock frequency increases, this gives us an opportunity to get more performance by pipelining. And as soon as we start pipelining, all of the hazards that you learned about or issues that you learned about in CS61C, like control hazards, data hazards, structural hazards become a thing, and everything about the microarchitecture changes. So as a consequence of device scaling, it wasn't just that we kind of changed microarchitecture incrementally along the way, it really changed the face of microarchitecture from something rather simple to something much more complex and rich and nuanced. So, technology influencing architecture. At the same time, a lot of this is done through the lens of programmability and compatibility with different applications in the marketplace. So this is really kind of like a three spokes on a wheel. You have applications benefiting from computer architecture benefiting applications. You have computer architecture driven by device scaling and the underlying technology and changes in manufacturing processes. And then you have this tug of war between these forces and what should the system look like to ease adoption to as large of a domain of applications as possible while simplifying the programmer's life as much as possible. I don't know if anyone here has had the pleasure of taping out a chip, but a rat hole that one falls into when taping out a chip is if you design this chip to be programmable, you design it to be programmable with an abstraction, with a programming abstraction that seems to kind of make sense at the time that you're designing the chip, because designing a chip is very difficult to do. There's a lot that can go wrong, and you kind of just want to get it out the door. Now, when you do that, and the next person comes along to actually try and do something useful with your chip, they will be cursing at the programming interface that you have left them. So how to get compatibility with architectural innovation without breaking previous applications, enabling new applications is kind of also a first-class citizen. Okay, so we said how architecture was driven by technology. Now I want to say something about what drives the technology. So this is, who here has heard of Moore's Law? Okay. Do they go over like the original Moore's Law paper in CS61C, or do they just kind of define it as like more devices per chip over time? Just kind of, yeah, it's a thing, it's a hockey stick shape, and it's leveling off is probably like the three things that they say. Okay, so this is kind of at a very high level what Moore's Law looks like. What it's fundamentally about is cost per operation over time, and saying how we've been able to kind of keep costs level while performing a significantly larger number of operations. And it's been kind of going steadily for the past 75 years, and it's finally starting to trail off, but it's really been kind of underpinning the innovation in computer architecture from the device side. Now, I want to go into a bit more of a deep dive and kind of really look at what Moore's original paper said. So if this has been done in CS61C, feel free to tell me and we can kind of skip over it. But in lieu of that, I thought it might be an interesting throwback history. So these are the two main graphs that came from Moore's paper. I'm guessing that if you've seen in the popular press one of them, you've seen this one. But actually, the main graph in Moore's original paper is this one. And from this, you can call this his observation. This graph is kind of the inference based on the observation. So I want to say a little bit about what the left-hand side means and point out kind of the two salient characteristics about it, and then why the right-hand side makes sense. So what Moore observed over several technology generations was that if you think about an integrated circuit as being kind of like a rectangle that you can kind of like ship, and it's made up of transistors which are used to build logic gates, and those are composed together to build larger functionalities. There's an interesting relationship between the cost of this thing that you're shipping, the overall integrated circuit, and the number of transistors that are on the integrated circuit. What he found was that if you have an integrated circuit, there's kind of a fixed cost to ship it. You can imagine it's like an inch by inch, and if you say to a circuit manufacturer, build me an inch by inch integrated circuit and put one transistor on it, they're going to say, okay, the cost of doing that is 10 cents. If you tell them, here, I want you to create this 1 inch by 1 inch integrated circuit for me, and now it has two transistors on it, which is to say only a small number of additional transistors, they might come back to you and say, okay, instead of the cost being 10 cents, the cost is 10 cents plus 0.0001 additional cents. Which is to say that there's kind of this upfront manufacturing cost of getting these chips out the door. And while you're like, let's suppose that all chips are 1 inch by 1 inch, it behooves you to add more transistors to this 1 inch by 1 inch IC because you can get them at a much smaller marginal cost and as a result get more functionality per unit cost, or to decrease the unit cost of an individual transistor. And so if you kind of put that together, you get one of these curves. So let's look at the top left curve, like the 1962 curve. So the x-axis is the number of components, which is number of transistors. Whenever we see components, just imagine that it's transistors. And the y-axis is the relative manufacturing cost per transistor. You get this nice amortization effect where if you pile on additional transistors, the amortized cost per transistor starts to dip. So as we go out on the left we go out towards the right on the x-axis, the cost starts to drop. So we get this kind of drooping. Now, eventually this no longer holds because if you have a 1 inch by 1 inch integrated circuit for a fixed transistor size, you can only pack so many transistors onto it. And after packing enough transistors onto it, packing an additional transistor starts to cost more. And eventually the cost just becomes infinity. So this curve dips down at first as you travel along the x-axis, but then it very quickly ramps up again. And so what you get from that is that there's a sweet spot if what you're interested in is the unit cost per transistor, and that's just the min of this trough, of this shape that we've kind of carved out. So his first observation was that because of upfront manufacturing costs, there's a sweet spot which is not at the origin on the x-axis, but kind of reasonably pushed out, which suggests that really you want your devices to have a good handful of transistors or components in them. At the same time, what he recognized was that if you sketch out that same curve over several technology generations, so now we see it at 1965 and 1970, not only is the curve shifting to the right, but it's shifting down. So what that's telling you is not only that the optimum number of transistors per IC that you should put on each IC that you want to be manufactured is increasing because it's moving to the right, but that cost itself is dropping. It's like a double whammy. So these were the two kind of salient characteristics that he pointed out, that the optimal number of transistors per device from a cost perspective was increasing, and that optimal cost was dropping. And if you take your finger and you put your finger on the minimum point of each of these kind of bell curves, and you kind of trace out the shape, his inference or his prediction was that through socioeconomics and human nature trying to derive a minimal cost per unit, plus the fact that the cost was actually dropping, that the number of components per IC manufactured over time would increase exponentially. So this is kind of the full story of Moore's law. Suffice to say, it started with an argument over cost. It didn't start as an argument over the number of ICs per device, because without that cost rationale for doing so, it still wouldn't make sense to pile more ICs per chip. But it's great that that happened that way. And kind of as an interesting side effect and coincidence of Moore's law, so this graph is a little bit imprecise. All this graph predicts is that the number of ICs per device is going to be increasing over time. What it leaves out is that, well, if the number of ICs per device is going to increase over time, for all we know, that could mean that our IC size, I was using like a 1" by 1" integrated circuit IC, just as the example, could just grow forever. But just incidentally, because of how this technology works, that's not what ended up happening. We lived in a world where, for the most part, the IC footprint was to stay the same, which would mean that as time goes on and the number of ICs per device increases, what that necessarily means is that the components or transistors per device shrinks. And as yet another fortuitous side effect of devices shrinking, this is what gave us almost all of the benefit of Moore's law. Devices shrinking, the effect of the speed of light between devices decreased, which allowed us to increase the clock frequency, which allowed us to pipeline, which allowed us to invent more sophisticated microarchitectures to take advantage of those higher clock frequencies, and the rest is history. Okay, so where does that leave us? So we have computer architecture. We have computer architecture being driven by device scaling. We now have a little bit of a sense for why device scaling happened the way it did. How does all of that translate into overall system performance over time? So here's, interesting. The text is also garbled on my slide. Well, you don't need to really pay close attention to these numbers, these numbers and letters. These numbers and letters are just representing different processors that have come out over time. I hope everybody can see this. This is a little bit more important. So this is 22%, and this is performance efficiency of single-threaded applications over time, like 22, 52, 23, 9.3, 2.5. So device scaling is a thing. How does that reflect on performance? So we can kind of study this over time relative to the VAX 11, which is like an early machine. And the shape looks kind of like this from 1980 to 2015. The salient characteristics is that it's sloping very sharply like a hockey stick, and then it's kind of leveling off. So what is happening here? It's suggested by Moore's law being a hockey stick on his original prediction slide. You'd expect it to just like go up and to the right, but something is happening here. We're getting kind of like different slopes as we go. So where is all of this coming from? So to kind of start things off at 1980, and there's kind of two pieces to this. There's the device scaling piece, and then there's the microarchitecture and applications piece. How well are microarchitects able to exploit the device scaling? And on top of the microarchitecture, is the software compatibility sufficiently good so that it can actually take advantage of that new microarchitecture? So I said two pieces, maybe we'll call it three. So between 1980 and 1985, things were primarily driven by device scaling. So transistors were shrinking, clock frequency was getting better. Because clock frequency was getting better, we could just get basic operations done quicker. And microarchitecture had most definitely taken off, but there were a few impediments that we'll learn about more as the class goes on. For example, the difficulty in improving the microarchitecture of CISC ISAs that were they're getting in the way of what would eventually become the golden era of microarchitecture and device scaling. So we were getting almost all of this 22% per year, a lion's share of it from device scaling. Then things took off for a good 10 to 15 years. We saw per year roughly double what we saw before. Does anybody know why things picked up in like 1985 to the 90s to the early 2000s? What caused the pickup? whether it was device scaling or microarchitecture or software innovation. And yeah. And what is your name? Ronan. Okay. Clock frequency was a part of it. Clock frequency was continuing to increase, which was definitely paying off. But it was also increasing here. So what happened between here and here to get us that jump? And I have something more to say about that in a second. But any other takers? Does anybody know? Yeah. What's your name? Nice to meet you. Yeah, that's a part of it. That's a part of it in an indirect way, which I'll say more about in like 10 seconds. Anyone else? Yeah, not quite yet. Soon. Hold that thought in your head. We're going to get to multicore in like 10 years. Yeah. CMOS had actually been around all the way in like the mid 80s to the 90s. CMOS has been with us this whole time. Good answer, though. I mean, CMOS technology continues to kind of improve at a steady clip. It's started in the 70s and it's kind of continued since then, but it didn't radically change in the 90s. Yeah, I'm going to say that as kind of the root answer. But what everyone else said, applications, kind of is derived from that. So in the 80s, we had the RISC and CISC debate. CISC being a style of instruction set architecture with more advanced instructions that kind of do more of your program in one shot, and RISC, where the philosophy was that your program should be expressed as sequences of simpler instructions. One of the reasons why RISC won the day was because compilers were getting more sophisticated. That would be my brother, who maybe wants to inform us as to some of the nuances in the RISC and CISC debate. Compilers were getting more sophisticated. As compilers were getting more sophisticated, their ability to decompose larger applications into these simpler operations as opposed to more complex operations. So for example, if your application was matrix multiply and your CISC ISA only exposed the matrix multiply operation, the compiler's job was relatively simple. It did nothing. But if your RISC ISA instead just allowed you to express multiply, add, memory load, store, conditional branch, it was more on the compiler to do this translation. So compilers evolved and matured. RISC became more of a thing for the reason that compilers were evolving, but for also several other reasons that we'll study more in the course. And as RISC started to become more popular, innovations in the microarchitecture became more realizable. It turns out, and we'll see why later in the course, that pipelining enables a paradigm for building microarchitectures to exploit something called instruction level parallelism, where you have very simple operations and not all of these operations depend on one another, which means that you can run them in parallel with respect to each other and decrease the wall clock time of a given batch or program's worth of instructions. And so as you got RISC, you got the ability to optimize in the microarchitecture better. It became a playground for microarchitects to design higher performance pipelines. And so actually this kind of shift between 1985 and 2003 was kind of two forces at the same time. One was more sophisticated compilers and people being able to express algorithms more efficiently in the native machine code, which of course improved performance, but also that microarchitecture and instruction level parallelism took off. And this was out of order execution, branch prediction, prefetching, all of the techniques that we're going to learn a lot about later in the course. And it took us all the way until like 2005 2003 or so. Does anybody know? And the right answer had been said a little bit earlier. What happened at 2003 to cause things to start to slow back down again? We start to see us go from 52% per year to like 23% per year. Yeah. Yeah, things got too hot. So kind of another way to see that is, so this is a picture describing a superset of what we saw on the previous slide. So the previous slide you can think of as like the blue dots on this picture. You kind of see the same kind of leveling off trend. It also shows several other trends. And in particular, look at where they started to level off relative to single thread. So what do we have? We have number of transistors. This is Moore's law. It's basically a hockey stick. We have single thread performance, which is the trend that we saw previously, which is starting to level off. We have processor clock frequency, which is kind of like a hockey stick, and then it levels off very quickly. Then we have power. This is the power envelope, the thermal device power of a given IC or integrated circuit. And then finally, we have the number of cores. So what I want you to pay attention to is which of these trends start to slope off first. That's going to be a hint as to what was the lead domino that caused the rest of this process to get going. So any observations on this chart? Say again? Frequency? Did frequency start first? It's actually quite hard to tell in this picture. Any other takers? It's definitely leveling off, kind of leading single thread performance, but was there anything else? And what is your name? Farhad? Okay, Farhad gave us the answer. So the answer is power envelope, our ability to cool or power these processors. So if you look very closely, the curve is so kind of slight that it's kind of hard to tell when it really starts to turn because it's like turning the entire time, but it's kind of like bending towards a complete, like a flat line from the very beginning of when the data started getting recorded. So you can kind of think about that as like an 18-wheel semi-truck where the brakes are in the front of the truck only. So you've got power kind of slowly tapering off. That's like me applying the brakes at the front of the semi. And what you see, if you look closely, if you look at the hockey puck shape of the frequency, it's kind of like at a 45-degree angle, and then all of a sudden, it kind of careens to a flat line. That's kind of like the back wheels of the semi-truck not realizing that the brakes have been applied until a few years after the level off occurs. And then all of a sudden it's like, oh my gosh, the frequency was a major predominant source of the power consumption in these machines. We had a little bit of headroom through which to increase the frequency without kind of really rubbing up against the ridges of our power envelope. But as soon as we hit that ceiling, we had to stop and write fast. At about the same time that this level off occurs, we see, or like a year or two afterwards, if you look closely, you see the number of cores start to increase, which we'll get to in a second. And putting it all together, single thread performance has not completely leveled off. We've been fighting tooth and nail to keep it increasing, but this is where it really starts slowing down. So going back to our picture, what started in 2003 was these front brakes of the semi being applied and us kind of losing steam on being able to, with reckless abandon, increase the clock frequency. So as a consequence of this, going back to the slide once in the future, we did what? Somebody said it. They were 10 years too soon. Yeah. Uh-huh. Yep. We go to parallelism. It turns out that if your application can be decomposed into different parallel parts, that you can get a lot of the performance that you were getting from a monolithic pipeline that was exploiting instruction level parallelism with instead application and thread level parallelism. So what we did was say, okay, instead of increasing the clock frequency and inventing better microarchitecture to kind of rate match that frequency as the number of like pipeline stages kept on increasing, we're going to go to our application and we're going to explicitly carve out parallel parts of the application. And nominally, if you can divide your application perfectly in half and run both halves in parallel, you get a factor of 2 speed up, nominally, ideally. And what I just said does not require any increase to clock frequency. You can keep the clock frequency the same and you'll still get the exact same thing. So we go to multi-core. And so that lasted for a few years until about 2011. And then things started slowing down even more, despite the fact that we had gone to multi-core. What happened here? Anybody know? Yeah. Amdahl's law was a major part of it. So if you've ever, we're going to go over this a little later in the class, if you've ever designed a parallel program and say managed to parallelize it by a factor of n, you probably didn't get a factor of n speed up. So there's a principle called Amdahl's law, which tells you counterintuitively how the small percentage that you can't parallelize, which exists in every application, is going to be the limiting factor in how much speed up you can get through parallelism. We used an example: if you could perfectly parallelize your application into 2 halves, you'd get a factor of 2 speed up. Just to put a slight twist on that example, if only half of your application could be parallelized, and you could freely parallelize to any degree that you wanted the remaining half, the maximum performance improvement that you'd be able to get from parallelism is this factor of 2. Because you can think of the runtime of your application being split into 2 parts. One part is not going to change, it's still that 1/2. And then the other part gets dragged to 0 as the number of cores or the degree of parallelism that you're able to exploit goes to infinity. So it's this kind of counterintuitive, if you're not able to parallelize or reap the benefits of parallelism across the entire app, you're going to be fundamentally limited. So people made the move to multi-core, but eventually multi-core started running out of steam, either due to the applications being fundamentally sequential, our inability to express them as different parallel segments, etc. So as a result of this, things started slowing down even more. At the same time, Dennard scaling was drying up. Dennard scaling was this truly, I say was because it's most, regardless of what we say about Moore's law slowing down these days, Dennard scaling is most definitely dead. Dennard scaling was this beautiful fact that as transistors shrunk in size, so recall Moore's law said that for a fixed IC area, we would expect more devices, more transistors, which means that transistors would necessarily shrink. As transistors would shrink, that the power or the switching energy, the amount of energy that it took to perform basic operations on those transistors would also shrink. That's what Dennard scaling said, which is truly amazing, because what it implies is that for a fixed die area, you can put more and more transistors, but the overall cost to do operations on that fixed die area would stay the same in terms of energy, which means we could actually power these chips. So Dennard scaling had all of a sudden stopped in the mid-2000s, and now even more, even though Moore's law kept on going ahead, we could pile more and more transistors onto these chips. We doubly could not cool the chips, because the additional transistors that we would put on would turn into additional energy tax. So this kind of slowed things down even more. And then the most recent kind of epoch in this journey is more of this, but also exacerbated by Moore's law starting to dry up. So Moore's law is a statement that the number of components per device would double roughly every 2 years. If you take that statement at face value, Moore's law has stopped, because the amount of additional transistors that we are piling onto ICs per unit time is slowing down. It has not stopped completely. We are still shrinking transistors, but it is slowing down. You couple that with steadily increasing Amdahl's law effects, increasing the fact that Dennard scaling is dead, and things are slowing down even more. And so this all, if you put it all together, has kind of led to an upheaval in computer architecture design. After 50 years of Moore's Law kind of ruling the scene, it's all of a sudden slowing down. In addition to that, we have Dennard scaling basically stopping, which means that as we pile more transistors on, the power that it takes to feed the chip is going up as a function of the number of transistors as opposed to staying constant. Amdahl's law is limiting performance. We still don't really have a competitive replacement to CMOS. CMOS has been a fantastic technology for the last 75 years, but its replacement is not soon on the horizon. And so we're not expecting to get a big hockey stick of improvement or a big step function of improvement from device scaling changes. And now energy is constraining everything that we do. And what this has kind of led to, the macro effects, is that the free lunch of software design is officially over. In the 90s, we were able to, through very clever pipeline and microarchitectural design, in a software transparent way, improve our computer and our program performance by about 52% every year. You could run the same program on steadily increasing device generations and see this speed up. This free lunch is over. Not to say that we can't get performance improvements, but just to say that what we have to do to get them is more in our face. We have to think more about parallelism. We have to think more about heterogeneity. And we also, at the same time, of course, have to think about the different form factors that our devices are taking on and the different sets of constraints that those form factors introduce. That graph from 2 slides ago that showed the 52% steadily year on year was kind of desktop devices, or kind of like mainframe performance. Now we have a fractured marketplace, to say the least. We have mobile devices, which are dominated by kind of like one style of ISA, in addition to just kind of the computing substrate, CPUs, GPUs, XPUs, things like this. There's a number of accelerators and peripherals on these devices that kind of fall outside the normal mold that has been called computer architecture for the past 50 years. So accelerators for radio, for image, for video, for graphics, for audio, etc. Outside of mobile, but closely related to mobile, because all mobile interacts with it, is like warehouse scale computers or data centers. So this is like a giant room full of quote unquote server grade CPUs or server grade processors, which have a very different microarchitecture because their workloads are much kind of more throughput oriented. This is like, how do you service the maximum number of Google search queries per unit time, as opposed to how do you turn on a display for as long as possible before your device or wearable runs out of battery. It's dominated by another type of processor. It's dominated by different styles of ISA, mostly for legacy reasons. So this is like mostly dominated by x86 style CPUs. And it features a different but related set of accelerators to the mobile and embedded devices. This is GPUs, FPGAs, custom hardware for specific workloads like machine learning. And then you have embedded computing and IoT, ultra energy sensitive wearables, where how you think about basic operations has to change dramatically. For example, if you're running like on an embedded device, maybe the only thing that you can afford to do is bit serial addition, where you do a very simple operation 1 bit at a time. And because of that constraint, which is motivated by energy requirements or energy constraints, you have to rethink the way that you design the rest of the stack. For example, if your application needs to evaluate polynomials, which rely pretty heavily on multiplication, how to do that where the only thing that you have is a bit serial adder becomes a little bit tricky. And this is also kind of led to a really exciting development. So for people who are interested in taking this course because you're asking yourself, okay, what is my best prospect for employment after I graduate? All of this heterogeneity and hardware performance improvements not coming for free has led to kind of a really exciting revolution in the hardware industry, or should I say the software industry, where instead of having separate hardware software companies like we used to have, like back in the day, we had Microsoft, we had like Google, at least initially, these were thought of as software companies. Like Microsoft branded itself as like the first software company. Google, at least initially, was all about software. Instead of that, what we're seeing these days is vertical integration, where not only are companies that are predominantly software companies dealing with software, but they're also developing, they're starting to develop more and more their own hardware. And they're doing this using a variety of business models. So the Apple M3 is actual Apple silicon that they designed in-house. They're still having it manufactured outside of Apple at primarily TSMC, which is a fabrication plant in Taiwan. But they're actually designing this silicon in-house. This silicon is for running their workloads. They are doing this because they know that they can get additional use and value, a sufficient amount of use and value out of developing this in-house. It's kind of like they see it as a one-time cost where they have to build this chip, but once they build this chip, their entire computing stack, and of course they can tune the chip exactly for that, is sufficiently better so that the initial upfront cost of designing these chips is kind of worth it. Tesla, Cruise for Car, Amazon, Microsoft, FPGA farms. What's interesting is not only do you see more of this vertical integration, but these business models are all quite different. So like Apple does not give open cloud access for general computation on its Apple devices. At least it hasn't like hosted this as a service. It's really for kind of like running the Apple stack. Google has designed the TPU, gives you the ability to access the TPU through like a black box interface, but doesn't actually sell TPUs on the market. So this has led to not only a bunch of kind of vertical integration, but a bunch of like new business models for how to manage the distribution of hardware. And in terms of like what this has done to the hardware space, it's made the hardware space kind of like a lot more interesting, because every time you as a company decide that you're going to invest in designing your own hardware, you're doing that for a reason. You're doing that because you feel that you can customize the hardware in a way that's going to give you value over the cost of designing that hardware. So you see a lot of customization in microarchitecture, in processor packaging, in what goes in on the die. We'll go back to the Apple M3 in a few slides, but suffice to say, like there's a lot there which is built specifically for Apple. And as I said before, the end system value here is going to justify, or they wouldn't do it otherwise, justifies the cost of doing these designs. And getting back to what I said at the beginning of the slide, why this is so exciting for you as prospective hardware engineers is that back in the day, when that graph that showed 52% year over year of hardware performance improvement was first put together, the demand across N companies for hardware engineers, you could think of it as like O of 1. We only needed one company doing hardware design. Now, for N different companies doing software design, the demand for hardware engineers has increased to O of N. So not only is there significantly more demand for hardware engineers, but the types of architectures that you're going to be working on are like radically different from one another. It's not all just like building general purpose CPUs. So super exciting time to be a computer architect. Okay, so now we're going to give just a little bit of administrivia on the course. Before I say that, I just want to kind of give you a nice die picture of the class of complexity that you'll be able to understand by the end of the class. So this is, we saw it at the beginning of the lecture, the Apple M3. Here's the Apple M3. I just want to say a little bit about what this chip is doing and kind of the different macro course. So the Apple A3 is a big little architecture. So it doesn't just have multiple cores, it has multiple of different sized cores. And when I say core, I mean like a conventional CPU that is like completely general purpose, one that is very flexible in terms of data dependent control flow that it can perform, random access memory operations that it can perform, and arithmetic that it can perform. And in addition to that, the Apple M3 has like other cores that are optimized for doing other classes of applications. So big, little, it has a collection of performance cores, which are shown in the red. The performance cores share their own local cache, which is like a fast local memory through which they can make these memory accesses. There's also another set of cores, which are kind of more energy constrained. So going back to what we said before about like power constraining everything these days. So what Apple will do is be very clever about saying, okay, if this device is currently energy constrained, I'm going to run the same function instead of on a high performance core on a lower performance core. All of these share this thing called an SLC, which stands for system level cache. It's another level of cache, which has like different management policies because it's shared between the P cores and the E cores. Beyond that, there's display engines because most of these Apple devices need to drive a display as opposed to being like server chips. So this is like one place that we see optimization per what Apple's expected set of workloads is. These are like for iPhones and iPads and laptops. And so they'll usually have like a display engine, more I/O, Thunderbolt to manage like Apple peripherals and I/O, NPU, neural processing engine, specifically for accelerating machine learning applications. It's kind of like a matrix multiply accelerator. And then a large GPU on the top of the chip for running not only graphics workloads, but workloads that you can express in a pattern like OpenCL or CUDA, not CUDA for the Apple M3, but languages that allow you to accelerate programs with regular data parallelism. So quite a lot going on this chip. Okie dokie. So with all of that, now we'll do some quick course administrivia. Before I give this in one breath, any questions? Okie dokie. Let's see how quickly I can do this. All right. So this class has shared lectures in person. Everybody made it to the right place. Tuesday, Thursday, 11 a.m. to 12:30. So we'll be done in like 19 minutes. So lectures, oh, that's a bug. Lectures will start at 11:10 a.m. Berkeley time, like they did today. They'll be recorded and webcast. So I've got the Zoom on right now, and I'll also put the recordings up on the website. And if you're in 252, the at least initial lectures are optional, but I recommend that you attend just so that you kind of know that you're on the same page. And some lectures will only include the 252 material. So we'll have 2 midterms. The midterms are in class, so hopefully this causes as little upheaval as humanly possible. One on February 27th, one on April 11th in class. You've got the entire class time to do them. Some of the problems will be marked 152 only versus 252 only. This will be clearly marked. You will not get extra credit if you are a 152 student for doing 252 problems and vice versa. So pay attention closely to which of the 2 courses the next announcements apply to. 152 has problem sets. The 252 students are welcome to do them, but they will not be graded. 152 also has labs. The 252 students are also welcome to do the labs for self-learning, but again, they are not graded. 152 has discussion sections. Anyone is welcome to go to the discussion sections. We have 4 of them. I believe that there will be enough space for everyone. And they're not graded, so this issue of who should attend them is kind of a moot point. 152 also has a final exam. Instead of the P-sets and the labs and the discussion sections, even though anyone can go to those, and the final exam, 252A has paper readings, which appear every few weeks, that we as a kind of mini lecture, which is to say me and the 252A students will have like a discussion around at a special time that will be determined soon, kind of like a round table. We'll talk about the papers and write reviews for them as if we were reviewing them being submitted to a conference. 252 also has a course project with a final presentation and a paper. The final presentation will be held during some time during RRR week, and we'll do another poll to decide when that is so that it does not conflict with people's schedules. The paper will be kind of like conference paper style. Course conflicts. We don't submit or we don't support conflicts with other courses. So while the lectures are recorded as a way of getting supplemental material to you, in case you want to go back and review something, they're not meant to be a drop-in replacement to in-person lecture where you can ask questions and you're more engaged in all of that stuff. We're trying our best to minimize the chance that there will be a conflict where there's like, we're having some exam outside of class and another exam could conflict with it. The exams will be in class to try to kind of avoid that. And so as a result of that, we're not going to explicitly support conflicts with other classes. And any conflicts that you do have, please reach out to the course staff and we'll see if we can do something about them. Okay, so just in terms of logistics, so again, my name is Chris. We have a really great team of TAs to help support the class this semester. Are any of the TAs here? Raise your hand high or stand up. None of the TAs are here. I promise they are super dedicated. So we Coleman, Jinhu, and Raghav, who are graduate students here and helping us TA. We also have Joshua, Lucy, and Iran, who are undergraduate TAs. And finally, we have Ethan, who is a reader. And their pictures will materialize quickly, I want to say, on the website. I've been prodding them to submit pictures. As they get submitted, their pictures will appear. I promise that they do, in fact, have faces. So the lectures, like I said before, 11:10 to 12:30, in-person plus recorded. The reading discussion for 252A, I'll do a poll. We'll figure out when that's going to be so that it's convenient for people. 152 discussion sections. Here are the times. It's like Tuesday, 7 to 9 p.m., Thursday, Wednesday, or yeah, Thursday, Wednesday. You can go to whichever discussion you prefer. They are optional, they are not mandatory, but they should be helpful. So go to, again, whichever one that you make. The textbook is Computer Architecture, a Quantitative Approach, basically the latest Patterson and Hennessy computer architecture textbook. It's not the same as the lower division one that you may have bought for 61C. It's the quote unquote quantitative approach. I think that's like the key phrase. The reading the textbook is not mandatory, but it is suggested and encouraged. It's a great textbook. And alongside the lectures, we will put on the course calendar and syllabus what sections of the textbook are to go with the lectures. So just a little bit more administrativia. Web page, it's this thing. These slides are on the web page. I was going to say you can find the web page link by going to the slides, but the slides are only hosted on the web page. So hopefully one of those we'll be able to figure out. The lecture slides will be online and available roughly at 8 a.m. the day the class is going. So the lecture slides are on the website right now for today. And then be on the lookout for several polls. For CS252A, when the paper discussion will be held, the final project presentations for the CS252A project, and then finally Ed invites. We'll be doing, instead of Piazza, because my understanding is Piazza got deprecated recently, we'll be doing Ed for discussion, and the TA office hours will be up in the next several days. We'll try to kind of spread them out over the course of the week so that if you need help at any point, you'll be able to go visit a TA for office hours. Okay, very quick on grading. So CS152, the rubrics are different for these two subcourses. For 152, it's 15% problem sets. Feel free to discuss with other students, but give credit where credit is due. So if you worked with a group of students, credit them when you turn in the assignment. 25% labs. We'll go over what the labs are about in a second. But kind of at a very high level, they use architectural simulators and give you an opportunity to do some open-ended architectural exploration. There's 5 of them. You have to turn in at least 3, or it's just like an automatic F for the class. Again, this is 152 only. And then the rest of the course, and this is like the major part of the course for 152, are exams. 2 midterms at the dates that I said before, and a final. The 2 midterms are each 15%, and the final is 30%. In person during lecture, closed book, no calculators, no smartphones, no smartwatch, all that stuff. And based on the lectures, the readings, the problem sets, the idea is not to surprise you, but to just kind of reinforce what was taught in lecture. Problem set 1, lab 1 will be out at the beginning of next week, and the problem sets and labs will have shared slip days. So if you're not able to meet one of the deadlines, there will be like a fixed budget of slip days that you can use to turn in the assignments a little bit late. This is only for the labs and the problem sets. We cannot do slip days for the midterms, which is probably not a surprise, but I thought I might mention it explicitly. For 252, we have a little bit of a different grading rubric. We have 20% these paper readings. So again, this will happen at kind of a similar clip as the P sets for 152. We'll put papers that you have to read on the course website. You'll turn in reviews through Hot CRP, which is like the widely used conference review submission system. And you'll summarize the papers, and then we will soon after discuss them, you being like the 252A students and me, the instructor, and maybe the GSIs. The GSIs can optionally attend. I don't know what our likelihood of them attending is if they won't attend lecture number 1, but we'll see if they show up. We will see. So 20% paper readings, 30% exams. It's less than 152 because there is no final. So as a 252 student, instead of prepping for a final, you get to present your final project during RRR week and get let off the hook a little bit early. And then finally, last but not least, a substantial class project. So a substantial research project, you'll do it in pairs. This will ramp up towards the latter half of February and then continue until the end of the course. The idea is kind of like a research style project where you can pursue a high risk, high reward idea. And by the end of the semester, hopefully, there will be several ideas that people would like to pursue further and potentially turn into actual longer term research projects. But the idea is kind of wild and crazy ideas that you may not have the bandwidth to do otherwise in your normal day-to-day research because they're just like too high risk. So it should be a lot of fun. The idea will be to kind of like make it a mock research experience where you'll turn in a conference style paper at the end. You'll do a presentation, mostly to kind of check mark where you are and kind of reflect on what you did. Okay, quickly, just because it's kind of complicated, go over the crossovers. So undergrads cannot take 252. 152 students can participate in the paper readings, but they can't get graded for them. Just in general, if you read this list, you can, for the most part, participate in not your subclass. 152 students cannot get graded for 252 assignments, but you're happy to participate on your own volition. So we will not forbid you as a 152 student to do anything that 252 students do. It's just that we won't grade you on them. So do them if you have cycles, but you will not get credit, like extra credit. Okay, 152 labs. So there's 5 labs throughout the course of the semester. This is for 152 only. The first lab will be out at the end of, or I'm sorry, at the beginning of next week. Each one is about 2 weeks. Like we give you 2 weeks to do them. And all of them are kind of broken up into 2 parts. One is kind of a directed part, getting you familiar with the infrastructure, getting you familiar with microarchitecture and design. Most of the lab, however, most of the graded part of the lab is an open-ended kind of experimental type exercise where you can just do whatever you want within kind of like a sandbox of possible ideas. So for example, for the first several labs, like an open-ended assignment might be to implement and evaluate a microarchitectural idea, like change the pipeline in a way that you think will improve efficiency, and then actually evaluate whether it does improve efficiency. The amount of time it takes to do the open-ended part, which I think should take kind of the longest, is kind of like a day. So like allocate a solid day for it. You'll have like 2 weeks to do the labs. And then for checkoff, you'll write up like a short lab report of what you did. A short lab report being as opposed to an indecipherable like log file, which is like a dump of a simulator where you like print out the dump of the simulator and you walk the TA through the dump to kind of prove what you did. That's not what we're looking for. What we're looking for is like actually a polished report, both so that we can read it and so that you can get some practice in writing these types of things. One thing I will say about the lab reports now is we give about 2 to 3 weeks to do them, but historically there's been a problem where everybody tries to do them at the last minute. This might sound familiar, and because they require infrastructure that are run on shared servers, too many people are piling onto these servers, and the latency of a simulation run goes to infinity. So we are working on solutions to this problem. We're hoping to be able to kind of package and containerize the lab infrastructure so that you can actually run it on your local machines. But at this point, I can't promise that. I will keep you kind of up to date on how that is going. But there is an incentive to do the labs on the earlier side and not wait for right before the deadline, because we can't, unless there's evidence that literally the servers have been completely socked for the 2 to 3 weeks solid, and you started working on them in the first day and you still can't finish on time. Unless there's evidence of that, we can't do anything about, oh, you started 2 days beforehand and it's taking you a day to simulate 1 million cycles worth of compute. So just kind of be aware of that. Okay, I'm gonna say like 3 minutes left of just kind of finishing off the administrativia, and then we'll end for the day. Any questions on all of the administration? Everything is perfectly clear? Okie dokie. All right. Very quickly, I'm gonna just zip, sorry. Hey. We will be going through the wait list by the end of this week. Great question. Anyone who clears the wait list will just be a normal student and there will be no problems whatsoever. If you are not able to get off the wait list and you're stuck there and we just don't have space, we will see how many students that ends up being a thing for. I personally have no problem in giving students who didn't get off the wait list permission to get on ed, but let me get back to you on that, just because staff resources are finite and I'm not 100% sure if we'll have the resources to answer everyone's question, especially if they're not enrolled. Okay. Any other questions? Okie dokie. So I'm gonna end actually because I think we're 2 minutes out here. So next time what we'll do is we'll go over just very briefly some of the course infrastructure, Chisel, ChipYard, RISC-V. This is what you'll be using for the labs. Then we'll give a brief whirlwind tour of the history of microarchitecture, and then we will continue on to simple pipelines. Thank you very much. Hey,
Any of the discussion sections going to be recorded or
we hadn't planned on recording them. If you absolutely cannot make any of the discussion sections, let us know. and we'll make accommodations.
Yeah.
Yeah, no problem. Hey,
Like any estimate